randomized measurement for multi-parameter quantum metrology, and this is joint work with Senri Chen from Caltech. Okay, so first I'll expand the terminology here. So what do I mean by multi-parameter estimation? In this problem, we have a bunch of unknown parameters, which I denote by theta in your system, either classical or quantum. And what you do is you perform a bunch of measurements and sampling from a classical probability distribution. And from that distribution, you try to infer the value of theta from the measurement data. And the figure of merit we usually use in multi-parameter quantum metrology is called mean squared error matrix. It is this matrix which quantifies the covariance of the estimator theta hat to the true value theta. And our goal is to minimize this mean square error matrix in multi-parameter quantum metrology. So there's a famous bound called Cramer bound in classical probability theory. It actually puts a lower bound on this mean square error matrix. It describes the ultimate estimation limit achievable by locally unbiased estimator in those type of IID experiments. So the lower bound is pretty simple. It simply says V, the mean square error matrix, is lower bounded by the inverse of Fisher information matrix, which is a function of this probability distribution. And in terms of the applicability of this bound, it only applies to unbiased estimator, or more broadly, locally unbiased estimator. That means if you try to estimate some parameter in the vicinity of some local point theta 0, and you want your estimator to be exact at the point theta 0 and in its neighborhood up to the first order. So if this condition is satisfied, then this Cramer bound holds. And also, the Cramer bound is also achievable in the sense of if you use a maximum likelihood estimator and repeat the same experiment so many times, in the end, you can achieve a mean square error matrix that scales like I inverse over n. So that is the attainability of this lower bound. So basically, this notion called quantum Fisher information can characterize the sensitivity of a multi-parameter metrology experiment. Okay, so now let's take a closer look at the definition of Fisher information matrix. So Fisher information matrix can be viewed as a second-order derivative of this infidelity function here. Okay, so it basically quantifies the difference between a probability at a point theta with the probability distribution at a point theta plus d theta. So it is kind of like a local property of the behavior of a probability distribution at theta. And the exact expression is given on this slide. So it is simply the expectation value of this so-called logarithmic derivative function. And okay, so clearly, like the larger the Fisher information is, the better you can do multi-parameter sensing. And you can generalize this entire framework to the quantum case by introducing this so-called quantum Fisher information matrix. So you can interpret that in two ways. The first way is you can interpret that as the second order derivative of this quantum infidelity. And it quantifies the change of a density matrix around the local point theta. And in another case, you can also look at its exact expression. So it is basically the expectation value quantified by this so-called symmetric logarithmic derivative, which is simply generalization from the quantum case from like a vector to a operator. So using this notion called quantum Fisher information matrix, we can have this quantum Cramer bound that applies to quantum metrology experiment. So it says that the mean square error matrix is lower bounded by the inverse of I, which is the classical Fisher information matrix, but also lower bounded by the inverse of the quantum Fisher information matrix, which is larger than the classical Fisher information matrix. So what exactly is the relation between the classical Fisher information matrix and the quantum Fisher information matrix? Like, are the Cramer bound achievable in the is the Cramer bound achievable in the quantum case? So now let's take two different situations. The first one is a single parameter estimation. So if we only have one parameter we care about in your quantum system, then what we do is we can perform a different type of quantum measurement. For example, M1, M2, M3 on your quantum state. And it gives us like a classical Fisher information matrix. And you can actually pick out the optimal measurement you can perform on your quantum state. And this, you can verify that this would give you like the exact definition of the quantum Fisher information on the previous slides. So to summarize, in single parameter estimation, the quantum Fisher information is simply the maximum classical Fisher information optimized over all possible measurement on the quantum state. However, in the multi-parameter situation, the case becomes more complicated because you might have some optimal measurement that gives you the best performance regarding estimating θ1. And you might have a different type of measurement that gives you the optimal precision for θ2. So different type of measurement, they might not commute with each other, and you cannot perform them in your experiment simultaneously. So as a result, quantum Fisher information can be strictly quantum Fisher information matrix can be strictly larger than the classical Fisher information matrix. So there might not exist some POVM that allows you to achieve the quantum Fisher information matrix over this type of single copy measurement on the quantum state. So how do we resolve this issue? Does that mean like quantum Fisher information matrix is no longer useful in multi-parameter metrology? So there are several ways to deal with that. So one way is to introduce a notion called collective measurement. So previously, I show measurement only on one copy of quantum state. But now if you allow like infinite number of copies of your quantum state and you allow like a joint measurement on these copies of state that might be entangled across different probes, then you can actually have this asymptotic attainability of this quantum Fisher information up to a factor of 2. So to explain this expression a little bit here, I introduced something called a weight matrix. So it is basically a matrix that put importance on different parameters you try to estimate. And then I use trace W dot V, where V is the mean square error matrix, to quantify the performance of a multi-parameter experiment. And then this expression here basically shows that when you have infinite number of copies of your system and you do collective measurement, then apparently you can achieve this quantum Fisher information matrix up to a factor of 2 using like this classical Fisher information matrix. So here you're optimizing over all measurement that applies on the all the copies of quantum state. And apparently there are like 2 drawbacks of this protocol. One is that it requires like a very large experimental resource because you don't always have like the ability to do like collective measurement on all copies of state. And also here you need to introduce this weight matrix. So it has to be fixed before you try to optimize over different measurement. And luckily, if we restrict the discussion to only pure state instead of general mixed state, we have a better result. So one result is using this Fisher's notion called Fisher symmetric measurement. So by Fisher symmetric measurement, I basically mean the situation where the classical Fisher information matrix is proportional to the quantum Fisher information matrix. And in terms of pure state, if you do like tomography of pure state, and the number of parameters is 2d minus 1, then the optimal coefficient of this proportionality is 1/2. And you can actually find some measurement that achieves this relation, which is I equal to half of j. However, the problem is this type of measurement are usually have a very high implementation complexity. For example, like it's exponentially large circuit complexity, because M is derived based on knowledge of psi, and or in other situations it might be like it has to be like hard random. So it means you have like infinite number of measurement outcome, and it is almost infeasible in practice. So a solution to overcome this implementation complexity is to introduce like 2 copies of quantum state. If you have 2 copies of pure state and you do a joint unitary to design on the quantum state, you can actually achieve this saturability of this quantum fission information matrix. So in that case, if you just use 2 design, the classical fission information matrix would be equal to the quantum fission information matrix. But again, it is not entirely ideal because still you need like 2 copies of quantum state, and you need to do a joint measurement on the entire system. So this work aimed to actually solve this problem. So yeah, sorry, before I go on to the next slide, so I just want to mention there's also like a no-go theorem going on over here, which says that there's no like single copy measurement or individual measurement with a finite number of outcome that can achieve this relation, which is I larger than half of J for all pure state. So basically, these 2 kind of situation is like you cannot just expect that you find like a universally optimal measurement, for example, like 2 design measurement on a single copy to achieve like this Fisher symmetric condition for 1 copy. Okay, so our work, we actually take a step back and we ask, can we still achieve like a very good performance using like efficient measurement, but maybe we don't want exact optimal coefficient. And this is our conclusion. So basically, we prove that if you use like a randomized measurement, which is like 3 design, you can actually achieve a pretty good performance where the classical fission information matrix is larger than the quantum fission information matrix by at most a factor of 1 over 4. So it is only like 1/2. Has a 1/2 gap from the optimal coefficient. And moreover, it goes around the previous no-go theorem in the sense that we only use like single copy measurement, and the performance are near optimal for all pure states. So it is not state-dependent measurement. And we also can have definitely like finite number of measurement outcomes. So yeah, so we believe that this would be like more experimental, accessible in practice because we no longer need like 2 copy measurement or like very difficult like individual copy measurement for this multi-parameter estimation task. Now I'm just going to briefly talk about the proof idea behind this result. So the idea is quite simple. We just try to convert this problem of parameter estimation to the problem of learning quantum observables. So here's how we do that. We first define a bunch of estimators, which is simply a map from the measurement outcome to the true value of theta. And we call it like local shadow estimator because it is only optimal in the sense of it is efficient in the vicinity of a local point theta 0. So it is not globally optimal. And it also uses a notion called classical shadow. So as you can see here, our estimator is simply the trace between some observable we call deviation observable that we are going to define later, and a rho hat, which is an estimator of the quantum state. So it is simply the classical shadow estimator, if you know the details. But basically, it is some kind of estimator of quantum state that can be obtained from a 3 design measurement. Okay, so now once we define this local shadow estimator, we just need to find out what is the locally unbiased condition on this deviation observable that they need to satisfy. And then we can calculate the mean square error matrix as a function of x. And finally, we try to pinpoint what is the most efficient x we try to use in order to both satisfy the locally unbiasedness condition and also achieve the optimal mean square error matrix. So we find out like exists a construction of deviation observable so that the mean square error matrix is lower bounded, is upper bounded by a constant times J inverse, where J is the quantum fission information matrix. And from the Cramer bound, we also know that the classical fission information matrix, the inverse of the classical fission information matrix is the lower bound of V. So in that way, we build a connection between the classical fission information matrix and the quantum fission information matrix, which allows us to prove the previous result on this slide. Okay, so yeah, now I'm just going to move on to talk about one example or like an application of our protocol. So this example involves fidelity estimation of a pure state. So usually, like in a task of fidelity estimation, we don't know exactly what kind of quantum state we have. But now we show that if we impose the constraint that the state is actually a pure state, we can achieve better performance than some traditional method. So now our answer is that the state is simply a superposition between phi, which is the fiducial states we try to project to, and then the other part is 1 minus f, which represent the infidelity of this quantum state. And f is the fidelity we try to estimate. So now we compare different estimator. The first estimator is simply a projection onto phi, which is actually the optimal estimator you can use for any fidelity estimation task. And the optimal mean square error matrix here is f times 1 minus f is actually the minimum amount of value you can achieve. However, the difficulty about this approach is it is not always easy to perform a projection onto phi in practice, especially when phi is like highly entangled state or like non-Clifford states, then we don't know any efficient way to do that projection. So we can instead use our protocol, which only use 3 design measurements, and our shadow estimator. So as our previously already shown, this mean square error matrix here is only a constant away from the optimal value. That it means it is at most like 4 times f1 minus f. So it might sound like, okay, can we get a better constant, or is this the optimal protocol? So we can actually compare that with a standard shadow estimator, which is we simply try to derive the classical shadow from the measurement outcome, and then we sandwich that by the projection onto the state phi. And then we can try to calculate the mean square error of this type of estimator, where we don't use any knowledge of the quantum state. In this case, we can show that the mean square error matrix actually has a very large gap between the previous 2 examples. So especially when f is very close to 1, that means your state is very close to your ideal state. Then the mean square error in the first 2 cases converges to 0. That means you can have a very precise estimation, but in the last case, you still have like a constant as the mean square error. So now to summarize how exactly we do the second type of estimator, we actually need like kind of 2 steps, because we know like our local shadow estimator is only optimal at the vicinity of its true value. So it is not local, it's not optimal in the global domain of theta. So we actually need to do like 2 steps. The first step, we need to obtain a coarse estimate of theta, and you can do that by, for example, just use the classical shadow estimator. And in the second step, you start to use this local shadow estimator once you have a coarse estimate of your unknown variable f, and then you just keep compute the deviation observable using the updated value of f, and then you keep update the value of your local shadow estimator and repeat that many times until the result converge. So here's our simulation result. We compare the performance of local shadow estimator to the standard shadow estimator. And as you can see, the performance of the numerical simulation match very well with our theory prediction. So in this example, we try to use an ansatz where it is a pure state characterized by 4 different parameters, and which represent the probability amplitude of a pure state. And we pick a fiducial state, and then we try to estimate the fidelity between that and the 4 different unknown states. That's why there's like 4 data points here. And you can see when the true infidelity converges to 0, that means when the fidelity of the state becomes higher and higher, there's a more gap or larger gap between what we can obtain from the classical shadow and the local shadow estimator. So yeah, and in our experiment, we also, because we need to perform the experiment so many times until we converge, so we predict the mean square error as the kind of the inverse of the quantum efficient emission divided by the square root of n. And then that part also matched very well with the theoretical prediction. Okay, so yeah, so to summarize, in this work, we've shown the power of the randomized measurement for multi-parameter estimation for pure state. We also have some results on approximately low-rank state. That includes, for example, like noisy pure state, and some class of mixed state where you have like very large number of parameters to be estimated. And you can find that on like our archive paper. And some future like unsolved question involved this project is, for example, can we use simpler measurement protocol? Because here we still need to do like global 3 design. Like can we use like maybe local poly measurement or like approximate 3 design to still achieve the similar behavior of our protocol? And also, for example, how do we actually calculate this local shadow estimator? Because now we need to calculate the trace between some observable xi and this rho hat obtained from classical shadow, and that is not always possible. So that's also another open question. And that's it. Thank you for your attention.